Okay, moving right along with our EChem discussion. This was the last slide we've left off on, so we're now in lecture 5, and hopefully get a chance to finish up this lecture right here. Make sure you add that last statement. I forgot to click that right at the end. Equilibrium lies far to the right, and that will show you, get you on the right slide right here. Okay, so here we have a scenario where we're going to be making something called electrolytic cells. Those are the ones where you have to plug them in to make them work. Delta G is greater than 0. They are not thermodynamically favored. So highlight this first line and then highlight these last two statements. The anode will take electrons from one species. They take them. And the cathode will kind of forcibly give them through getting some sort of power source. For example, if you were to have this molten NaCl, you could hook it up to a power source, and what's going to happen is on the negative terminal of the battery, the electrons are going to go toward the cathode right here because they're going to be gaining electrons. Red cat, that works out. And so what you'll do is you'll take that Na plus ion, and you can actually make like liquid sodium. They cool that off. This is one of the ways they manufacture sodium, is from salt, all right, by using electrolysis. So kind of interesting. What if you needed some chlorine gas? Here's what you do here. At the anode, the electrons will be leaving. You're losing electrons, and then it completes the circuit here, and then you get the chlorine gas. Okay, now this is where these problems get a little bit tricky. So if you're looking at the reduction, this will be understood a little bit better on the next problem, I think. If you're looking at the reduction, there are two possibilities of what could happen. Reduction could be a positive ion or water, all right? And the species with the most positive and least negative would be the one that is being reduced in this reaction. So if we put calcium iodide and ran power through it, we know that the water is going to kind of take over the reduction reaction. And this is one that will be given to you, I'm sure, but the reduction reaction is the one that produces hydrogen. The oxidation reaction of water is the one that produces oxygen. So these either one of these guys could be the oxidation. Now this might be a little confusing to you, the fact that they circled the smallest number, but remember these are oxidation number. You always give E0 red values. So these are both, you could flip those and turn those into E0 ox numbers if that makes that easier. As a matter of fact, go ahead and do that. Write E0 ox equals negative 0.53 volts, and E0 red of this one equals negative 1. E0 ox of this one equals negative 1.23 volts. And then you go, okay, so we pick the bigger number just like we did on that one. Okay? And then that will tell you what would happen when you put calcium iodide, and you know which one is undergoing oxidation, and that's the one that loses electrons, remember. So the electrons are over here. So what will happen is those, and this could be a way of making solid iodine or hydrogen gas. Well, that's hydrogen gas, pretty easy to do with water under many circumstances. So probably in this instance, they'd be using calcium iodide to make solid iodine to sell. But at the other cathode, the calcium has nothing to do with it. It's the water that ends up taking over, and you bubble off hydrogen gas, and then it becomes more and more basic as you do this. Okay, so these are kind of tough problems. So here is a really good example of 4 reduction potentials given, and really all you're doing is applying a current to a copper 2 bromide solution. Now, what is really going to be going on? This is our last problem for this unit, but it is pretty intense here. So when we're looking at the water, remember the hydrogen is the one that tends to compete for reduction. The oxygen is the one that tends to compete for oxidation. So when it says what is the reduction half reaction, there are 2 candidates for that. One would be the water reaction right here. Now notice what we did is just find out that that's the one that has the hydrogen in it, so we write that out. Now, how did we know between the other 2 right here which one was going to be the reduction? The copper is the one that why did they use copper here? Just a minute here. I gotta stop and think. Sorry about that. So when we're looking back to the previous slide here, what you want to look at is the positive ion. That is the one that, so that's the other thing. So really, really highlight that. This is something I forgot until I get a little rusty on these problems sometimes. So you want to look for the positive ion and not the E0 values. I got caught in that little trap right there. So so the positive ion is going to be the one that you will include, and then you just look at them and you say, okay, choose the most positive, least negative. So guess what? That's going to be the answer to problem A, which was what is going to be your reaction for the reduction. Okay, so here's what they did for you is change the other reactions into oxidation reactions. So you can see the electrons are on the correct side for being oxidation reactions right now, and you can see these 2 numbers are both negative, whereas over here, here's the one that had the oxygen in it right there. That was positive, and then this is the negative ion, and that was also positive. So we had to flip the signs of both of those guys, and then you want to choose the one that is more positive. So this one has bromine is going to be the business part of this. So this water didn't come into play at all in this reaction, but the type of problem that you would get on AP test is very similar to this, given these things. So you just have to look at it step by step and go, who's winning here on the reduction? And again, I want to emphasize that positive ion for reduction. Okay, lost an electron. Are you sure? I'm positive ion. Okay, so 2Br minus gives you Br2 plus 2 electrons. So now we have both our oxidation and reduction reaction from the previous one, and then you can write the overall reaction. You can see that we are gaining and losing 2 electrons, so those will cancel out, and that becomes our overall net ionic equation for this problem. And then it asks you to find E0. So E0 red plus E0 ox. Remember, you got to flip the sign of the oxidation one, and we had already established that, yeah, this is the oxidation right there, but and and we had already flipped the sign when we did that problem. So that's negative 1.0 volts, and then it ends up being an E0 value that's negative. And since we're doing an electrolytic cell and not a battery, it should be negative. So you're very glad that it's negative. It's thermodynamically unfavored. Electrolytic processes are never thermodynamically favored. All right, so you got to use electricity to drive the reaction. So get that all recorded, and then we have to find the delta G equals NFE0. Why don't you try this one on your own and see how you're doing with this stuff, finding these numbers. Hit the pause and give this one a try and finish on a good step here. All right, so let's see how you did. The N is 2 because when you look back at this right there, the 2 electrons and 2 electrons, that's why N was equal to 2 there, in case you were wondering. And that's a constant, and we just figured this guy out. That's joules per coulomb, or volts, and we end up with delta G that's positive, meaning not thermodynamically favored. So these electrolytic cells will always have positive delta G values as well. And ladies and gentlemen, you are now one little lecture packet that we're going to take 2 days to do from being finished with all of this wonderful material. Okay, so this is some good tough stuff here that'll keep you on your toes. So hopefully you're getting challenged by this nice hard material here, and we are now done.